Hello viewers, welcome to my channel KK Concepts of Electrical Engineering.
Pointing vector and power flow. Pointing vector is defined as P equals to E cross H. Both are vector quantities, so cross product of vector is again a vector, and E is electric field intensity, H is magnetic field intensity, and the units for E is volts per meter. Similarly, H is amps per meter. This is nothing but volt amp per meter square. So units for P is volt amp, which is nothing but watts per meter square. So watts per meter square represents power per unit surface area or power density. So these are the units for power density. Hence Poynting vector is in the nature of power density. So we have P equals to E cross H, which is nothing but EH sine theta, and theta is the angle between E and H, and we have seen in wave propagation the angle between E and H is 90 degrees, that is nothing but theta equals to 90 degrees. Then this will be equals to EH, since sine 90 equals to 1. Pointing vector P is equal to magnitude of E and H. So the direction of P can be obtained on the basis of right-handed screw rule, and it is perpendicular to both E and H. So in vector form we can write this P equals to E H U N, which is unit vector normal to E and H. Then the direction of En is in the direction of wave propagation of the electromagnetic wave. En unit normal vector, and it is in the direction of wave propagation. Now let V equals to velocity of wave propagation, Un equals to velocity divided by the magnitude of velocity, scalar magnitude of V. Then Poynting vector P bar equals to EH V, then scalar quantity of V, watts per meter square. So this is our Poynting vector, instantaneous Poynting vector. So we know that Poynting vector is P equals to V cross H. The electric field intensity E and the magnetic field intensity H may be a time variant or time invariant. If E and H are independent of time, then P represents the constant power density, that is rate of propagation of energy per unit area occurring continuously. If E and H are time varying, an instantaneous Poynting vector may be defined. Let the variations be assumed as sinusoidal, then E of t equals to real term of E of x e to the power of j omega t. E of x is the complex vector function of position, and it is given by E of x equals to er plus j ei. This is real part and this is imaginary part. Therefore, E of t equals to real part of er plus j ei of e j omega t. Then this can be written as real part of er plus j ei cos omega t plus j sin omega t. Now only I am considering real part, then this will be er cos omega t, and if I multiply this term with this term, then j part is there, so imaginary, and this one again imaginary, and this one, so negative ei sin omega t. Similarly, if I find h of t equals to hr cos omega t minus hi sin omega t, then instantaneous Poynting vector P of t equals to E of t cross h of t. Now substitute these values. So er cos omega t minus ei sin omega t cross hr cos omega t minus hi sin omega t. P of t equals to ER cross HR cos square omega t plus EI cross HI sin square omega t minus of ER cross HI plus EI cross HR sin omega t cross omega t. This represents instantaneous power flow per unit area and is termed as instantaneous Poynting vector. Average Poynting vector. We know that average power is obtained by integrating the instantaneous power over one full cycle, that is time period, and divided by the time period, that is average power P average equals to 1 by T integral 0 to T P of T dt. Now similarly, if you find the average for Poynting vector, that is 1 by T of integral of 0 to T PR cross HR cos square omega t plus integral 0 to T Pi cross Hi sin square omega t minus integral 0 to T Er cross Hi plus Pi cross HR sin omega t cos omega t. For the first term, the result is half Er cross HR. For the second term, the result is half Ei cross Hi. For the third term, the result is equals to 0. P average equals to half, I'm taking common, then Er cross HR plus Ei cross Hi. Now, this can be written as half real term, that is Er cross HR plus Ei cross Hi plus J Pi cross HR minus Er cross Hi, which equals to half real term Er plus J Pi cross HR minus J Hi. This term is P of x and this term is complex conjugate of H of x, that is H star of x. P average equals to real part of E of x. I'm just substituting the values cross H conjugate of x. P average equals to half real part of E of x e to the power of j omega t cross H conjugate of x e to the power of minus j omega t. This term is nothing but E of t and this term is nothing but H conjugate of t. P average equals to half real part of dt cross H conjugate complex of t. Or simply we can write P average equals to half real part of E cross H conjugate watts per meter square. This is our average Poynting vector. Half E cross H conjugate is complex Poynting vector. The real part of complex Poynting vector is average Poynting vector. The instantic impedance eta equals to E by H. It is a complex quantity. Then from this E equals to eta H. You get E average equals to, if you substitute that, half real part of H eta H conjugate watts per meter square. Let H equals to Hm e to the power of minus j omega t, where Hm is the peak value of H, then H conjugate is equals to peak value of H e to the power of j omega t. Then H conjugate equals to Hm square. Putting this in the equation, P average equals to half Hm square PL pot of eta watts per meter square.
If you have any suggestions and queries, please mention in the comments. If you like this video, please like, share, and subscribe. Thank you for watching the video. Please stay tuned for more videos.